All right, let's talk about the invisible world that every single pilot has to master. We're talking about the chaotic, super powerful, and sometimes really treacherous weather that happens right next to the ground. This is our office, and understanding these forces, well, it's not just theory, it's survival. I absolutely love this quote. It just perfectly frames our reality, doesn't it? We live and fly at the bottom of this massive ocean of air. Think about it. Every single instrument in your cockpit, every little movement of the controls is just a reaction to the immense weight of that ocean pressing down on us. So here's our flight plan for today. We're going to start with the most basic force there is, the weight of the air itself. Then we'll get into how differences in that weight create wind, and why that wind moves in some pretty weird ways. After that, we're dropping down into the friction layer, our arena, and we're going to confront the most dangerous thing in there, performance shear. And finally, we'll wrap up with some critical local winds and some man-made hazards like wake turbulence. Let's start right at the beginning. Everything in weather, everything from a gentle breeze to a full-blown hurricane, it all starts with one simple idea: atmospheric pressure. It is the engine that drives the whole machine. The easiest way to think about it is like a pile of blankets, right? If you're at the very bottom of the pile, you feel the weight of all the blankets on top of you. Well, that's us. Here on the surface of the Earth, we're feeling the most pressure from that entire column of air stretching all the way up to space. So how in the world do you measure an invisible force? Well, the classic way is with a mercury barometer. And the principle is actually pretty simple. The weight of the atmosphere pushes down on this little pool of mercury, and that forces it up into a vacuum-sealed glass tube. So higher pressure pushes the column higher. When you hear controllers say the pressure is 29.92 inches of mercury, they are talking about a literal length measurement. That's how high the air's weight can physically push that column of metal. Pretty cool, huh? Now, throughout your career, you're going to see a few different units for this. In North America, we're all about inches of mercury for our altimeter settings, but you'll see hectopascals, which are the same as millibars, on all the aviation weather maps. And hey, if you're flying in Canada and listening to the radio, you might even hear kilopascals. The key thing, the thing you have to know, is this standard equivalency right here. 29.92 inches of mercury is the same as 1013.2 hectopascals. That is the absolute bedrock for setting your altimeter correctly. Okay, so now we get pressure. But what happens when that pressure isn't the same everywhere? Well, that difference creates wind. But here's the thing. That wind doesn't just flow in a nice, neat, straight line from high to low. Oh no, it follows a very specific and kind of counterintuitive set of rules. The main driver is something called the pressure gradient force. The best way to picture it is to think of a weather map, like a topographical map. High pressure is a big hill and low pressure is a valley. Naturally, air wants to slide downhill from the high to the low. So when you see those isobars, the lines of equal pressure packed really tightly together, that's a steep hill, a steep gradient, and that means strong winds. If they're spread way out, it's a gentle slope with light winds. Simple as that. So the pressure gradient gets the air moving. But then there's a twist, literally. As the Earth spins, it creates this apparent force called the Coriolis force. A good way to think of it is trying to draw a straight line on a spinning turntable. Your line is going to curve, right? Well, in the northern hemisphere, this force deflects moving air to the right. And eventually, the outward push from Coriolis balances the inward pull from the pressure gradient. And what's the result? The wind ends up flowing sideways, parallel to the isobars, circling around highs and lows instead of just crashing right into them. Okay, so let's bring all of this high-level physics down to where we actually live and fly, the boundary layer. We're talking about roughly the first 2,000 feet off the deck. This is where all those nice, tidy rules of airflow get really, really messy. This is our arena for takeoff and landing. See, down here, the air is constantly dragging against trees, buildings, hills, you name it. This friction is kind of like trying to run through waist-deep water. It slows the wind down a lot. And here is the absolute key. By slowing the wind, friction weakens the Coriolis force. This lets the pressure gradient force start to win that tug-of-war again, causing the surface wind to angle across the isobars, flowing into low-pressure system. Now, what's really important and frankly deadly serious about this layer is spelled out right here in the Royal Canadian Air Force Weather Manual. This isn't just some academic exercise. The manual states it directly. Aircraft have struck the ground and crashed because of a specific phenomenon in this layer. This is exactly why we study this stuff. And that phenomenon, that killer, is wind shear. It's just an abrupt change in wind speed or direction. But in the boundary layer, its effect on your aircraft's performance can be absolutely catastrophic. Okay, so shear basically comes in two flavors. You've got increased performance shear. This is when your headwind suddenly increases, your airspeed jumps, your wings get a sudden boost in lift, and hey, your performance improves. But then there's the other kind, decreased performance shear. This is the bad one. Your headwind dies or your tailwind picks up. Your airspeed plummets, lift just vanishes, and your performance goes right into the toilet. This is the killer the RCAF manual is warning us about.
Let's just walk through this. Imagine you're on final, perfectly on the glide path. Bam! You fly into an increased performance shear. All of a sudden, your airspeed spikes, lift surges, and your aircraft balloons upwards, way above the glide path. Now you're high, you're fast, and you're fighting this long float, maybe even risking overshooting the runway. It's manageable for sure, but it completely destabilizes your approach.
Now for the dangerous one. Same scenario. You're on the glide path, but this time you hit a decreased performance shear. That headwind you were counting on just vanishes. Your airspeed decays instantly. Lift disappears. The aircraft starts to sink like a stone, way below the glide path. In a split second, you are low, slow, and sinking with a terrifyingly high angle of attack. The risk of undershooting the runway or even stalling right onto the ground is immediate and very, very real. So shear is obviously a huge deal, but it isn't the only hazard lurking near the ground. The boundary layer is also home to some incredibly powerful local winds created by terrain and an invisible danger that we actually create ourselves, wake turbulence. Let's take a look at a really powerful local wind, the Chinook, which you'll find on the leeward side of mountains like the Rockies. This is not just some warm, dry breeze. A Chinook can cause the temperature to jump by 20 degrees Celsius in just a few minutes. That incredible release of energy generates extreme, violent turbulence and severe wind shear. This isn't just uncomfortable flying. It's the kind of force that can actually overstress an airframe. It's a serious threat. And then you've got wake turbulence. Every single aircraft generates lift because of a pressure difference. You've got high pressure below the wing and low pressure above it. Well, at the wingtip, that high pressure air is always trying to escape and curl up around to the low pressure side. When it does that, it creates these powerful invisible tornadoes that trail behind the aircraft. So, what is the most important thing to know here? You need to know when these vortices are at their absolute worst. You have to burn this into your brain. The most intense, the most hazardous vortices are generated by an aircraft that is heavy, clean, and slow. Just picture a fully loaded 747 on final approach, wings clean, flying slowly. That is the single most dangerous wake-generating machine you can possibly encounter. This right here shows you the playbook for staying safe. So, since these vortices start when the nose wheel lifts off and they stop when it touches back down, our procedures are all about avoiding that specific block of air. When you're taking off behind a heavy, you rotate before the point where they did, and you make sure you climb above their flight path. When you're landing, you stay at or above their glide path, and you touch down beyond where their wheels touched. Always, always fly above and stay upwind. We'll end on this thought from the incredible aviator Beryl Markham. You know, the laws of physics that govern pressure and wind and turbulence, they are constant, they're predictable. The weather is just the dynamic, ever-changing result of those laws in action. And if we can understand those constants, we can learn to master the change, to stay ahead of the aircraft, and to navigate all the unseen forces of the boundary layer safely.